Hello, everyone. In this video, we will discuss integrals of vector-valued functions. Integrals of vector-valued functions. Suppose the derivative of an unknown vector-valued function is known, and it is also a vector-valued function. How can we find the unknown vector-valued function? Please consider the following 3D space. Consider the space curve of the unknown vector-valued function, where the arrowheads point to the direction of increasing parameter. A specific value of the parameter leads to a point on the curve. This is the position vector of the point, and this is the tangent vector at the point. Meanwhile, these are the position vectors and their corresponding tangent vectors at different points on the curve. The unknown vector-valued function is solved by integrating both sides of the equation above, and then applying the fundamental theorem of calculus, which will be discussed later. Therefore, this is the unknown vector-valued function. It provides the position vector of any point on the curve. The first term refers to the position vector of the point the curve has to pass through, which is also known as the initial condition. While the second term refers to the vector-valued function for the path or the trajectory of the point beyond the initial condition. In the following discussion, we will focus on definitions and how to determine the integral of a vector-valued function. Let us start with indefinite integrals. Suppose we have an antiderivative of a vector-valued function, which means its derivative leads back to the vector-valued function. The indefinite integral of the continuous vector-valued function is the antiderivative of the vector-valued function plus an arbitrary constant vector. Recall from our previous discussion that the derivative of a vector-valued function is the derivative of the component functions. Hence, the indefinite integral of a vector-valued function is the indefinite integral of the component functions, and it is also a vector-valued function. Next, let us define definite integrals. Suppose a vector-valued function is continuous on the closed interval a, b. The definite integral of the vector-valued function from parameter equals a to parameter equals b is the limit of the Riemann sum of each component function, as the number of subintervals of the sum approaches positive infinity. Provided the limit exists. The definite integral is a constant vector, or a vector with constant components, while an indefinite integral is a vector-valued function, which is a vector with functions as components. The fundamental theorem of calculus states that differentiation and integration are inverse processes. Suppose a vector-valued function is continuous on a closed interval. Let the antiderivative of the vector-valued function be differentiable on the corresponding open interval. This means that the antiderivative is defined as the following integral. Then, the derivative of the antiderivative, or the derivative of the integral of a vector-valued function, leads back to the vector-valued function. Now let us go the opposite direction. The definite integral of the vector-valued function, or the integral of the derivative of the antiderivative, leads to the antiderivative. Specifically, the difference of the antiderivative at the endpoints of the closed interval. Thus, we can conclude that differentiation and integration cancel each other out. and the result of successive application of each process is the vector-valued function where both have been applied. These concepts are valid whenever a vector-valued function is an antiderivative of another vector-valued function, including continuity and differentiability requirements mentioned earlier. Moreover, these concepts work for any antiderivative vector-valued function pair, regardless of what symbol or variable were used. Going back to the illustration earlier, we had the derivative of an unknown vector-valued function equals another vector-valued function. Here, the antiderivative is the unknown vector-valued function. And we want to find its equation, given the point in space it must pass through and the vector-valued function of its tangents. Integrate both sides of the equation. On the left side, there is an integral of a derivative. So by the fundamental theorem of calculus, it is equal to the difference of the values of the unknown vector-valued function at the two limits of integration. On the right side, the variable u is just a placeholder for parameter t. Rearranging leads to the equation of the unknown vector-valued function. And it can be found by integrating the tangents, and making sure that the resulting smooth path passes through the point of the given initial condition. Example 1. Evaluate the definite integral. Solution. We can solve this problem by evaluating the definite integral of each component function of the vector-valued function. For the first component function, integrate using an inverse trigonometric function rule. Then evaluate using the fundamental theorem of calculus. For the second component function, integrate using a natural logarithmic function rule with substitution. Let u be t squared plus 1. So du is 2t dt. Then evaluate using the fundamental theorem of calculus. For the third component function, rewrite the integrand first by polynomial division. And then integrate each term using a basic integration rule and an inverse trigonometric function rule. Evaluate using the fundamental theorem of calculus. Combine the three results into one vector. Thus, this constant vector is the definite integral of the given vector-valued function. Example 2. If we have the derivative of a vector-valued function, what is the vector-valued function that satisfies the following initial condition? Solution. From the fundamental theorem of calculus, we found out that the integral of a derivative of a vector-valued function leads back to the vector-valued function. Integrate each component function, and add an arbitrary constant vector. The indefinite integral can be written in the following equivalent form, where an arbitrary constant has been added to each component function. Because the given initial condition is for t equals 0, substitute t equals 0 into the indefinite integral. Next, to be able to solve for the arbitrary constants, equate each component of this vector to the corresponding component of the given initial condition. Solve for each value of the arbitrary constant. Then substitute these values into the indefinite integral. Hence, this vector-valued function is the particular solution that corresponds to the given initial condition. Example 3. Evaluate the definite integral. Solution. The integrand refers to the norm of vector-valued function, so we should use the formula for the norm of a vector. Because the vector-valued function is dependent on the parameter, its norm is going to be a function of the parameter. Simplify the integrand using a hyperbolic identity. Then use a trigonometric substitution. Let t be the tangent of theta, so that dt is the secant squared of theta d theta, and the square root of quantity 1 plus t squared is the secant of theta. Make the corresponding changes to the limits of integration. Then rewrite the new integral in terms of the new variable. For the purpose of showing a complete solution, integrate using integration by parts, although this can be done using a table of integrals. Let u be the secant of theta, and dv be the secant squared of theta d theta. This means that du is the secant of theta times the tangent of theta d theta, while v is the tangent of theta. Substitute the required expressions into the integration by parts formula. Replace tangent squared of theta using a Pythagorean identity. Then rewrite the integral into two integrals. Because we are back to the integral we are trying to solve, add it to the other side of the equation, and divide both sides of the equation by 2. Afterwards, apply a trigonometric function rule. Evaluate using the fundamental theorem of calculus. Therefore, the definite integral of the norm function is approximately equal to 1.15. While integration denotes an infinite sum, this number does not refer to the infinite sum of the norms of the vector-valued function. However, this number refers to the arc length of the space curve defined by a vector-valued function, from t equals a to t equals b, whose derivative is the vector-valued function inside the norm. Given the derivative of the vector-valued function, through integration, we can find the vector-valued function whose length from t equals 0 to t equals 1 has been computed. Please refer to a separate discussion about arc length and curvature for more details and examples. Example 4. Differentiate the integral. Solution. Let capital R be the whole integral. Then write the vector-valued function inside the integral in linear combination form. Before applying the fundamental theorem of calculus, apply a substitution in the chain rule. Let u be equal to t squared, which means du dt is 2t. By chain rule, the derivative of the integral becomes the following product. Now we can apply the fundamental theorem of calculus because the upper limit of integration is just a variable rather than a function. Substitute the required expressions. And simplify. Recall that the square root of a squared quantity is the absolute value of the quantity. Hence, the derivative of the integral is the following vector-valued function. Example 5. Find the length of the arc defined by the following vector-valued function. From t equals 0 to t equals 2. Solution. From Calculus 2, the arc length of a curve in 3D space defined by a set of parametric equations is given by the following formula. Differentiate each component function, and substitute the results into the formula. Then simplify. The polynomial inside the square root is a square of a binomial. Recall that the square root of a squared quantity is the absolute value of the quantity. From t equals 0 to t equals 2, the expression inside the absolute value is always positive anyway, so we can rewrite the integrand without using the absolute value. And then integrate each term using basic integration rules. Evaluate using the fundamental theorem of calculus. Therefore, this is the length of space curve from t equals 0 to t equal 2. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.